So I should, I think this one. Yeah. So can you see?
Yes, we see. We can see.
Okay. So for Bruno, I am saying that this is Kuchara-Gacha theorem according to Levin. And so please interrupt me, and especially people who are not very well accustomed with this Kuchara-Gacha story. Maybe you should be aware. You should be awake and tell me when I'm saying something unclear.
And also, please share the whiteboard.
The address of the whiteboard. Okay.
And also, you need to turn sharing on, I guess.
I didn't do this.
This blue, in the upper right corner. This
no,
blue.
I can. On this share. Yeah. Sharing on. Change to anyone with the link and edit. Okay, done. So where is the link? Sorry. Copy link copied. So we should have somewhere.
Never heard of Kuchara. I'm not sure, but.
Sorry?
No. I'm just saying you are saying that for those who are not familiar with this Kuchara-Gacha story. I mean,
yeah.
I'm just saying that I never heard of.
Oh, Kuchara. You are ideal. So you are, but you are a bit too clever. But
no. I mean, I'm saying that I haven't heard of.
Yeah. Okay. So please tell me immediately if something is unclear. So, okay. So I think I sent the board to the no.
Yes.
Yeah.
Yeah. So theory. Yeah. Oh, great. So what is the Kuchara-Gacha theorem? So this is let alpha be an arbitrary sequence of zeros and ones. And then theorem says that there exists a random sequence, Martin-Löf random sequence, such that alpha is Turing reducible to omega. It was proven first, I think, by Kuchara and then by Gacha, but Kuchara paper is somehow is recursion theory paper, so nobody knows what is there. And Gacha just wrote that every sequence is reducible to a random one. So everybody first learned this from Gacha. And so there are two things. First, what is Martin-Löf randomness? And second, what is a Turing reducibility? So no, Martin-Löf randomness maybe I'll speak later, but Turing reducibility, we can say that there is an oracle machine.
Sorry, and we cannot change quantities. We cannot say that there exists some Martin-Löf, some sequence that's for every alpha reducible to algorithm. This is not.
This is not true, of course, because by cardinality arguments, the number of alphas is continuum, and if omega is fixed.
Okay.
Yeah. So, but we can say that there exists an oracle machine that maps omega to alpha, which means, or in other words, if given omega is an oracle, it computes alpha.
Mm-hmm.
No, it's a bit strange. Of course, nobody would expect that if we have some, I don't know, some uncomputable sequence, we would not expect that it will be computable with random oracle. Of course, if an oracle is chosen at random, there is probability 0 it will compute a given non-computable sequence. But still, if we choose a very special Martin-Löf random sequence, alpha will be still reducible to omega. So it's somehow kind of paradoxical and even maybe unpleasant thing, because it says that for computability with random oracles, we cannot, it's important whether we understand random oracle is in probability theory sense or in logarithmic sense. So this is the big difference here. So if we have an oracle machine, it has a tape, and on this tape we write omega, and then the machine reads omega and then prints bits of alpha one after another. So if we have a machine, then for every contents of the tape there is some output. So machine gives a mapping of, I don't know, infinite sequences of zeros and ones which are written on the tape here, to formally we should say that could be finite or infinite sequence. And this is the statement of Gacha-Kuchara theorem. Okay, so is it clear?
So this is both for finite and infinite sequences, right?
No, no, theorem for finite sequences is
okay,
trivial,
right.
because of course every finite sequence can be computed without even oracle.
Right.
It's not there is no reasonable question. But for alpha infinite sequence, it contains some information, and so it can be computed or computable or not.
Maybe just to clarify, is it equivalent to saying that there is an algorithm that, given any index, computes, index I computes alpha y, given oracle access to omega?
Yeah. And of course we can just no. If it's infinite sequence, then it's the same, because if we consider partial things, maybe there is an algorithm that computes all even terms, but doesn't want to compute any odd terms. So then we cannot transform it into an algorithm which writes from left to right. But
sorry, if you have an algorithm that computes odd terms and an other that even terms, then you can combine them.
No. If we have just a machine is defined on even alpha and on odd alpha, and is undefined on even alpha, we cannot transform it into a machine which writes alpha sequentially. Yeah. I'm saying trivial thing, that the presentation of output as a term of sequential writing the bits or computing a given bit can be important if we consider finite, non-everywhere defined things. But if we are interested only in everywhere defined alpha, sequence alpha without infinite sequence without gaps, then computability in all sense of the word is the same. It doesn't depend on anything.
Yeah.
But here alpha is everywhere defined. It's infinite sequence.
Yeah. Alpha is everywhere defined. It's an infinite sequence. So it's exactly the same thing. We can confirm that this is the same meaning. That doesn't matter at all.
Sorry, am I right that the reducibility can be considered universal?
So we can say that the pair is there exists an oracle machine and there exists a Martin-Löf random sequence. So can we fix the machine in advance?
Yes.
And so you can explain why we can. It's true. Why we can.
Well, I think we can prenex the sequence by the codification of a machine.
Yeah, we can
Somehow,
construct universal machine, so to say. So first it reads the prefix of the sequence, which is an encoding of the machine, and then it says that interpret this code and simulate this machine. So this machine can be universal in the beginning, and then every Martin-Löf sequence, of course, remains Martin-Löf random if we just add a prefix, which is an encoding of any prefix, in particular encoding of the machine. Okay, and so there is another interpretation of this. So let me speak about different thing, which is a kind of plan how we can prove this theorem. But let me start with a different thing, which is called image randomness. So we have now a definition of oracle machines. We will consider them as mappings, computable mappings of the set of all infinite sequences to the set of all finite and infinite sequences. So this is infinite, it's finite plus infinite. And then there is the following theorem. So imagine we have a composite thing. There is a random number uniform distribution, a generator of uniform distribution, and then it sends to computable mapping. So machine has internal perfect random bit, and then these bits are written on the oracle tape, and then this oracle tape is sent to oracle machine, and we get some output, which is a finite or infinite sequence. And so for each device of this type, we have some distribution. So if there's a transformation T, and this is uniform distribution P, their output has some distribution T of P. So for example, you know how to simulate, I don't know, Bernoulli distribution or normal distribution using a perfect random bit generator. So if you want if you want to have, I don't know, output not uniform but 1/3, 2/3, so it's still possible to do if your machine has inside the uniform distribution, you just simulate it. And so in general we can have different outputs. So now let's discuss the question, which distributions can appear as outputs?
Distributions on what?
So generally this has distributions or on finite and infinite sequences, because output can be finite. But let's look first on the special case when the distribution is on omega. So which means that with probability 1, T of omega is infinite with probability 1. So the finite strings have 0 probability, so it's actually distribution is concentrated on infinite sequences. So which distributions can appear as outputs? Can you say this? So for which distributions we can construct a probability, a machine, randomized machine with bit generator and transformation that generates this distribution.
I mean, you want to say something about, well, I guess about the probability of at least having, you know, if I have some finite string, you are asking what can be said about probability of this string occurring.
Yeah, so distributions on infinite sequences are defined by the probabilities of the cones. So what is the probability that the sequence starts with 0, starts with 1, starts with 0, 0, 0, 1. So actually,
I guess this should be like something lower semi-computable or how?
Oh, for general case, it's lower semi-computable. But for if, which means that probability that the output starts with x can be computably approximated from below.
Mm-hmm.
Because we can simulate the machine what it does with this random bit generation and this random bits and this random bit. So we just see how it behaves on different inputs and find the cases when it produces given output. And we just have to sum. Machine can use a lot of bits and can work for a long time. So we discover new things, cases when this happens. So this probability is can be approximated from below. It's called lower semi-computable. So the answer is that this probability of starting with a given x should be lower semi-computable. And if we know that it's a measure, so the finite strings have probability 0, then what is the answer then? What class of measures we get?
You mean if you know that your measure is lower semi-computable and it's
a measure.
Okay. I mean,
so then it's computable. Just you can compute the probability to start with any given string with arbitrary precision. Why? How do you do this? So you want to find probability to start with that the first bit is 0 and first bit is 1. What do you do?
Well, I guess you just start lower bounding probabilities for both zeros and ones until their sum is very close to 1.
Yeah. So if you have lower bounds and if you know that the limit values have sum 1, then of course we can. They are upper bounds at some point. They should be close, and then we know this with high probability. So we can say that the computable measure is just a measure which can be obtained by a machine. A probabilistic machine which almost surely produce an infinite sequence.
Mm-hmm.
And then we come to a philosophical thing which is called image randomness. So imagine we have such a machine and this machine produces some output distribution Q, and this is a computable distribution on infinite sequences.
So all finite sequences have probability 0.
Probability 0. And then you are told that this machine produces some alpha. And then, as usually, if a fair coin, you are told that fair coin produces 0, 0, 0, 0, you don't believe this because this is not random with respect to uniform distribution. So normally there is notion of Martin-Löf randomness with respect to a given computable distribution. And so it is just a sequence which are believable, which are plausible as an outputs of machines. So there are two answers when you will believe for this composite aggregate. First, if alpha is random with respect to output distribution Q. And just if you have a machine and you know that the output distribution of machine is Q, then you expect that plausible outputs are random with just sequences which are random with respect to this distribution. And another answer is that let's look inside the machine. So then machine T should be applied to some random sequence. So T of omega is alpha for some random omega. So, and philosophically, these things should be equivalent, because we should get the same kind of philosophical beliefs, whether we look under the hood of this device or we just consider the output distribution of this device. And this should be a theorem, and this is the theorem, and it's called image randomness theorem. And so the idea of how can prove Gacha-Kuchara theorem? You can prove it from image randomness. Imagine that we consider some universal T which can behave as any other machine. Then somehow every sequence should be random with respect to this T. And so it should be, if we have this theorem for arbitrary, not everywhere, not almost everywhere defined mappings, and we prove that alpha is randomness with respect to output distribution, then we will get Gacha-Kuchara theorem more or less for free. And somehow this is a plan which was unfortunately is not valid in this form, and Laurent proved that this cannot work like this, but Levin found a way around this problem, and somehow managed to do this. But I see that probably everyone is no, the things are familiar to people who worked with Martin-Löf randomness, but I'm afraid...
You know, as for me, I didn't get your point about universality of T. I mean, I thought, you know, to prove Kuchar good, you know, Kuchar-Gacha theorem, you could just, for any alpha, construct a probabilistic machine with respect such that alpha is random with respect to the output distribution of this machine. And this machine should be, you know, total. For
no, if it's no, you cannot produce. Not every sequence is random with respect to some computable distribution. This is the problem.
Okay, so then I don't even have an idea how could you
what it all means.
No, I mean, how then could you hope to prove Kuchar-Gacha theorem this way? I don't understand.
Okay, okay. So let's make a fresh start, and I want to explain what is a priori continuous probability.
Okay.
And also, you should say what is random relative to semi-measure.
Yeah, that's the problem, exactly.
Yeah.
Yeah, so what is a priori continuous probability? So we know that every machine corresponds to a lower semi-computable function.
By the way, I don't see you You are writing?
Yeah. I'm writing, but I didn't change this.
Yeah,
sorry.
sorry.
It's so what we should remember for previous things. So if we have some machine, then we have lower semi-computable function. Let's say machine, I don't know, t. Then we have some lower semi-computable function mt of x, which is the probability that output of t on a random input starts with x. So for every machine, we have some distribution on its outputs when the inputs is uniformly distributed. And more or less, we know that this function has this property that mt of x is greater or equal to mt of x0 plus mt of x1. Because if it's just, actually it's equality plus probability that the output is just exactly finite x. So if these two events, starting with x0 and x1, are parts of disjoint parts of this event. And there is more or less one-to-one correspondence. So if we have a lower semi-computable function which has this property, and also an empty string is 1, then we can construct a machine which produces such a thing. And this is Levin 1970 paper. So most of you were not even born, I guess, in this time. So it's a very old result. Zvonkin and Levin paper. And then if we take universal machine, which can imitate any other machine depending on some prefix, then the output function will be maximal lower semi-computable function. No, these properties are called semi-measure. So it will provide a maximal lower computable semi-measure.
Lower semi-computable semi-measure.
Yeah. So you can just if machine imitates any other machine with some probability, then this output measure will be of course greater than this with some constant that for any other machine. So it's this is just the general idea of Levin to define everything, to consider maximal objects in semi-computable classes. So this is called it's defined up to O of one factor. If we have two maximal measures, they are the up to constant factor, and it's called a priori continuous probability. So it's just this. And then there is a definition of randomness. So if we can now consider as a definition, or if you know another definition, then it will be a criterion, a characterization of randomness. A sequence omega is random with respect to a computable measure p, if and only if this universal semi-measure is not much bigger than p, so it's bounded for all prefixes of alpha. Let's write it alpha here. So what is the intuitive idea? So if we think that the sequence is really random with respect to p, then there should not be another distribution which produces the same prefixes of the sequence much better than P. So if universal semi-measure produces much easier, then the sequence is not random with respect to P. And we can also that's answer to the question of Bruno. So if let's consider if P is a semi-measure, we can just take it for a definition. So we can say that if there is some semi-measure and the random sequences are sequences whose prefixes are not much more probable under the universal machine than under our current machine. So this is the definition, and if so, we have this a priori computable continuous probability, then no M. And now, according to this definition, every sequence is random with respect to M. Because then just this ratio is equal to 1. So for trivial reason, it's formally
and this definition makes sense if P is Lauer semi-computable semi-measure.
Yeah. No, it doesn't make sense probably really because it doesn't have good properties probably. But we can, for our current purposes, we can temporarily consider as a definition.
Oh, but the proper, like if it satisfies Van Lambalgen criterion, it's not checked yet.
No, maybe you are right, and one can study something in this direction.
Yeah, I think it's a natural approach. So maybe somebody should write the paper and check some properties.
No, I would suggest doing things in the opposite order. You first check the property, then you tell us, and then you write the paper.
That's obsolete approach.
Yeah, so first you write the paper, and then you check.
Of course.
Maybe this paper proves this. And you send it to the conference, and the reviewer should check whether it's a proof.
Of course.
And if you write enough paper, then one of them will be approved. Yeah. And so here now I can completely formulate the theorem, which would be very nice but false. The only problem is it's false. So imagine we have a measure, uniform measure, and we have some machine T, and this is output semi-measure of this machine.
Please.
Yeah. Oh, yeah. Yeah, спасибо. Yeah. Okay. So false theorem is that we have a uniform measure and we have a machine which applies to a output of this coin distributed according to the machine. It has some output semi-measure. And then imagine we have alpha is random with respect to Q, which means now in our new definition that this ratio is bounded for the prefixes of alpha. And then there exists some omega such that alpha is T of omega, and alpha is random with respect to pp. And this also can be understood in the sense that this ratio is bounded for prefixes of omega. But this is a good definition of randomness, which is Martin-Löw's definition or any other definition, any other reformulation. So this is well-known thing, and this is what we defined right now as a definition of this. And it would be very nice if this theorem would be true, because it implies Gacha Kuchara. And this is, I'm trying to, Sasha, I'm trying to answer your question, where we are and what we are trying to do. So what at that point, what should be clear, hopefully, is that first, what is stated in this theorem, and second, that the theorem has two special cases. The first case, when Q is measure, and then it's true and it's image randomness theorem for measures. And also, Gacha-Kuchara theorem is a special case, because if T is a universal machine, then Q, which is T of P, is just equals to M. So M divided by Q is 1. So for every alpha is random with respect to this output distribution M. And so there exists a omega, which is a pre-image of alpha, that makes it and it's random with respect to P. Okay, so is it better now or not?
Yeah, I mean, yeah, I understand both the statement of the false theorem and how it implies.
Yeah.
You know, my question just was that I was suggesting then you probably will be saying are going to say that, you know, this false theorem is false. Yeah. And
no,
you know that.
No, long ago, Laurent, so for many years, I wanted someone to prove this false theorem and get a Gacha-Kuchara theorem as a consequence. But Laurent was so upset by my request that they finally decided to disprove this claim, and he said this is false. So actually, it's a false in a very bad way. It's in effect, there are two machines, T1 and T2, which produce the same distribution Q, but for them the classes of T1 of P and T2 of P are different. So the property of a being an image of a random sequence is not determined by the output distribution. So there is no chance to define randomness with respect to semi-measure to have to make this false theorem true. Not only our specific
Sasha,
definition.
What is in the corner? T1 of P
is not equal to T2 of P. So there are two machines
that produce the same.
They produce the same distribution.
Yes, but then T1 of P equals T2 of
P. But T1 of Martin-Löw random sequences is not the same as T2 of Martin-Löw random.
But that's not a counterexample. It needs to be disjoint.
No. So no, we somehow, if we can reasonably define randomness with respect to a semi-measure, to make the image randomness theorem true for semi-measures, then these things should be just sequences which is random with respect to Q.
So you are here implicitly assuming that we have a theorem that if we apply T to Martin law of random in the usual sense, then we get something which is random.
Yeah. No. I think that that this is true for that's exactly what the false theorem claims, that we can we define the randomness with respect to semi-measures and have the same the image of random sequences should be just the sequences which are random with respect to this
I guess
semi-measure.
your false theorem just says it in one of the directions.
No. For this case, it's enough, of course, but really, I would like.
Sasha, and there is alpha. You're circling alpha in the bottom. It should be omega. It's random with respect to p. It's typo.
Yeah. So I think it's very confusing, everything. But I'm sorry, but. Okay, but is something clear now, or it's completely?
I mean, you are just saying that this false theorem is false, then okay.
Yeah, this is, but it would imply Kuchara very nicely, but this is false.
I didn't quite get about this T1, T2, but okay, I mean, it's not
No,
important.
the idea is that you cannot.
I also didn't get it.
No,
So
the
can
idea
you-
is not only our definition of randomness with respect to semi-measure, which is bounded, which is this definition. Not only our definition is bad, but we also cannot hope to get some other better definition for which this false theorem will become true. Because the class of possible sequences can be different even if the output distribution is the same. So there is no definition in terms of output distribution.
Oh, sorry, you changed the theorem that it should hold, that it holds, if and only if, right? I didn't, I missed that.
Yeah. Sorry. For Gacha theorem, we need in Kuchara we need one direction, but of course for being serious, we need.
But then, can you say? Could you say, please? This theorem is refuted, right?
Is refuted.
But it's refuted that it holds in both directions, or you can even refute one of the directions. I mean, does it make sense? My question.
Yeah. So maybe you say that this theorem can be saved in the direction we need for
Gacha Kuchara.
Gacha Kuchara. I should look at. I should look in the example of Laran. Maybe it could be, but this is not what Levin does. Levin saved it Levin saved it in one direction, but with additional requirement. So that's now at least.
Am I right that this theorem, if you take just Q equals M, this false theorem is equivalent to Gacha Kuchara theorem? I mean, if you take just one of the directions.
No, not exactly equivalent, because it's just a special case for M.
Yeah. So So probably it's true for M, your false theorem, but it's false for some other Q. Okay, I get it. Yeah.
Maybe it's false from some other.
Sasha, the other direction is always true. If amida is random, then its image is random with respect to image measure.
In the sense of this definition.
In the sense of this definition. And so Laurent's example proves that the direction we need is false, because the other direction is true anyway.
But can you explain why it's true anyway?
Because if you consider the set of sequences that are not random, then it defines it defines that they are non-random in, so to say, Martin-Löf sense. You can cover the set of all such sequence by a set of small measure. And if we consider the set of all omega such that they are mapped by that machine in that set, you obtain a set of small uniform measure, which is, so to say, effectively open. And so you obtain that the image is not.
Yeah, so it seems, yeah, indeed, it seems that in one direction it should be true of all. I just forgot about this. Yeah, you are right.
I mean, I didn't quite get it. I mean, so I'm trying to understand. So if you are saying if alpha is random, you map it to something, and
if
then
omega is random,
if omega is random, you map it to something
alpha,
by t.
then alpha is random in our definition, because
so
imagine
if
it's not,
then the prefixes are unbounded.
Then the ratios are unbounded.
Yeah.
And let's consider now all the points when this ratio is bigger than 100.
All right.
For example. And let's consider all the preimages of these points.
Yeah.
So let's consider all the random sequences which will induce this a sequence that has large ratio. And the claim is that these values of.
So you mean for some point, or infinitely? I mean all infinite sequences where.
So we consider all points when m divided by q is large. We consider,
I mean all finite sequences.
Okay, let me try to draw something. So we have our T is map sequences. Here we have measure P uniform, and here we have some a random omega is random, and then there is T omega.
So no, it's very easy property. The ratio of two measures is large can only happen on a small measure according to the bottom of the bottom part of the ratio.
So if let's imagine that this is not random. This means that it belongs to for every C it belongs to it has some prefix where Q is the image of P. There is some prefix where m divided by Q is greater than C.
Mm-hmm.
Then let's take all sequences when this m divided by Q is greater than C.
Mm-hmm.
And let's take a preimage of this set. And
yeah, I mean, you're saying that its Q
the preimage
measure is at most 1 over C?
Contains omega by our assumption and has a small P measure.
Yeah. I mean, on the right, the measure is Q measure is at most 1 over C, then by definition of preimage.
Yeah, the Q measure is at most 1 over C, because M is bigger. We can take the maximal cones and consider only the cones. So if M is much bigger than Q and M is still have some at most 1, then the measure is small, and so the preimage has small measure, and it's effectively open, because this is effectively open because M is lower semi-computable, and so we can
and Q.
And Q
Well, so you know.
and Q. Yeah, for random for measures it was okay, but indeed.
I mean, it's in a denominator.
Yeah, Kolya,
Right.
people don't found an error in your argument.
One.
Because we have to consider the set of here the set of sequences where the ratio is greater than C, and take its preimage. And
Yeah.
this should be effectively open. But here we have Q in the denominator, and Q is now a semi-measure. So we cannot claim that it's effectively open.
Yes.
So things do not work like this. One should consider them more carefully.
Right.
But
Okay,
now, at
okay.
least, let me explain the main idea of Levin. So let me erase.
Sasha, I think it does work.
But how?
Because can you not say that Q is larger than P, and eventually you're interested in M over P somehow?
No, M over P. No, M over P maybe not.
So eventually you need that M over P for all pre-images
But
is large.
M over P may be bounded or whatever. P is not related with Q. P can be much smaller or much bigger. Q and P are not maximal at all. So Q can be more than P and less than P. So not how it helps you.
But the universal machine also evaluates P.
No, T is not universal now.
No, but the machine is universal.
No, M is universal.
So the mapping T
now
is
we
not...
consider arbitrary mapping T.
Okay, sorry. Okay, if T is not universal, then indeed you're right.
No, if T is universal, then we have M divided by M. So we are in the Kuchera Gacha situation. So it's... No, but indeed, there is no counterexample to this false theorem in the reverse direction. At least one should check what happens in the Laurent example. But let me still. I see that I'm completely failing and everything is mixed. But at least let me try to say what Levin says. So let's consider only machines that use, I don't know, 2n plus O of 1 input bits to produce output bits. So they have some kind of limited use.
N output bits.
To produce n output bits, yeah. So in terms of this picture, if we take some string of length x and take of length string x of length n, then its preimage should be determined on the level 2n. So only 2n first bits are important to determine whether machine will output n bits on the output. So just when producing nth output bit, it is not allowed to look what is in the oracle above the nth position, 2nth position. So this is a special class of machines. And Levin made two remarks. A, machine of this class can generate a maximal semi-measure. So still, even if we restrict machines to this property, it doesn't prevent them to generate maximal semi-measure. And this is the first claim. And the second claim is for machines of this class, false theorem is true in our direction, in direction we want.
Could you, I don't understand. So you're saying that the machine uses 2n plus O of 1 input bits and O of 1 and for
Let's forget about O of 1. It will just 2n plus, I don't know, 10 or something. Don't. This is not, this O of 1 is not important.
You know, and for all n? Oh.
For all n, yeah.
For all input, okay, yeah, okay.
So it's just kind of a syntactical thing. If machine, unless machine is produced n minus 1 bit, we do not let the oracle tape, oracle head go behind the, above the 2n. So the machine gets access, needs, when machine produces first, initially machine reads some constant number of input bits, and then when it produces output bit, it's allowed to read two more input bits. Just special restriction on usage.
I mean, then I don't understand how you can show that there exists a universal, how you can generate maximal semi-measure. I mean, I guess you should read the description of the machine from some finite prefix.
No, of course, no, of course we have to generate maximal semi-measure not by universal machine. The machine is not universal anymore, but it still generates maximal semi-measure. So the semi-measure is just very close to the original one, but machine is now completely different. It's no more universal, of course. No, it's not. I don't claim that it's obvious. Neither A or B is obvious. But what should be obvious that if Levin proves A and B, then it can derive Kuchara Gacha.
This is obvious. So let's start proving A, say, or B.
Okay, Bruno, you are looking disappointed. So I have confused you or what?
No, I forgot why A and B implies Kuchara Gacha, but I will check later. Don't worry about it.
No. No. This is not the difficult part. So imagine we have special machines with limited use, with bounded use.
Yeah.
And they still can generate semi-measure, maximal semi-measure. And then if we can define this, if we can apply false theorem is true for them, then we could apply it without any problems and then construct a random preimage for every sequence. No, it's trivial. I don't, if you understand how the false theorem applies Gacha-Kuchara, then it's just the same for special class of machines.
Yeah, my problem, I'm disappointed because I have trouble remembering false theorem.
So false theorem is if the ratio for initial fragments is bounded, is the sequence is random with respect to a semi-measure in this stupid sense, new stupid sense, then it has a random preimage.
Okay. Yeah.
And so if of course if we replace our maximal semi-measure by either other maximal semi-measure, which is above just a constant.
Okay.
Then
I
of course
remember.
the ratio is the same, but also
so
bounded.
Then it's always 1 the ratio.
So it's not if for this it's always 1 for this machine, and then it's
okay.
And then let's see how to prove A and B. No, I am afraid that Okay, let's try. So, how to prove
but
A?
I think I know how you can prove A.
Oh, fantastic!
No, but I think so the idea is that you approximate.
First, let me write the statement. So, some bounded use machine produces maximal semi-measure.
But by the way, is it true for every semi-computable, lower semi-computable semi-measure?
No.
You mean that can produce a semi-measure which is by a constant factor different only, yeah? What is true for any computable semi-measure?
That it can be generated by bounded use machine.
Of course not. By bounded use, if machine is bounded use, that generated semi-measure on n-bit strings is a finite has only 2n digits. So of course, if you use only 2n bits to produce n bits, then the probability to get given n bits is just a multiple of 2 to the minus 2n.
Okay, but surely this doesn't hold for maximal semi-measure, this property.
Yeah, but no, so the claim is it can hold for maximal semi-measure. There exists a maximal semi-measure that has this property. So maximal semi-measure is actually not one semi-measure, it's a class of semi-measures.
Okay.
Up to the maximality is just constant up to factor.
I see. So in the proof we will construct a maximal semi-measure.
Yeah, I will construct a new maximal semi-measure, a new semi-measure which is maximal, and is generated by bounded use machine.
Okay.
And so now Bruno can explain how to construct such a semi-measure.
So the plan is to approximate all universal semi-measure with precision 2 to the minus 2n. Instead, so we know that the semi-measure is at least 2 to the minus n, and so we approximate with high enough relative precision. Is this idea?
So the idea is just take maximal semi-measure m of x, and then just approximate it from below by 2 to the minus 2n fractions, multiples of 2 to the minus 2n, on strings of length n. Just first we forget about the machine. We just want to work with a semi-measure. We want to construct maximal semi-measure, which will be on n-bit strings. It has only 2n digits. How do we do this?
But how do we know when to stop?
No, so a maximal semi-measure on x is just a kind of growing thing.
Okay, yeah. So whenever you obtain a new bound for your m of x, for the classical maximum,
as soon as m of x crosses the next threshold, we just increase this approximation. So the approximation.
We just take the rounding of this.
Take the rounding below.
Sasha, it seems that we do not even need 2n. We need only n plus some constant, right?
Not constant, really. Let's see like this. So we just, if we take this approximation, what are the problems?
I mean, maybe some problems could be with zero or something. I'm not sure.
No, with zero. What do you mean with zero? Just with empty string or what?
I don't know. So we want to show that in this way we get some measure which is semi-measure, which is maybe just a constant factor smaller than m of x, right?
It should be a bit smaller than m of x. So there are two problems: why it's a semi-measure, and why it's only a bit smaller than m of x.
Well.
So semi-measure means that we should have this, and now we have this approximation from below.
So my problem with zero is that if m of x is really small, so that
we will get zero.
Yeah, but maybe Bruno have said that m of x should be at least
since m of x is a universal machine, it should be bigger than any measure. So, for example, it's bigger than
2 to the minus n.
2 to the minus n, which is a uniform measure. So, in this way, we do not lose much, actually. If we use precision just a bit more digits than n, we are still okay. But what is the problem here, and how can we overcome it?
I mean, problem why it's semi-measure?
Yeah, why this it may be not anymore a semi-measure, because when m of x0 is smaller, and m of x1 is smaller,
and maybe the left hand side.
That's okay, because but the problem is the left hand side can also decrease, and the problem is it decreases not exactly synchronously with the right hand side.
Yeah.
Maybe m of x0 is okay.
So the granularity of the right hand side is much smaller.
Is much smaller.
And that means that we are allowed sometimes, if we find a little increase in the right hand side increases, but the granularity is not enough for the left hand side.
Yeah, but for m of x, so imagine that m of x0 and m of x1, they use some small granularity, so they already moved far enough to be rounded non-trivially. M of x0 is large and m of x1 is large, but for m of x, we have much bigger granularity, and so m of x is not enough to consider any non-zero approximation. So it's clear what is the problem. So if in the left-hand side we have smaller granularity than in the right-hand side, it will be okay. But since here the granularity is bigger, we are allowed only to make big increase. And for big increase, there is not enough material. So is it clear what is the problem or not? Sash?
Yeah, I mean, for example, if m of x just equals the sum of m of 0.
Yeah.
And when you approximate x0 and x1, you get much closer. You can get much closer to their actual values than x, because
they can just have their actual values if actual values are multiples of our small step. But the sum is not. So how, and now you
maybe you should multiply m.
There is a very simple way
by some coefficient which depends on its length, so that you can kill this possible.
No, it's much easier. So imagine we have a safety margin. So imagine we have this inequality with 2 to the minus x, for example. Not minus x.
I mean, I'm sorry, can I suggest my solution?
Yeah.
Can I just multiply, or maybe it doesn't work. If I multiply.
So Sasha wants multiplicative safety margin and Other Sasha wants additive safety margin, but I think both ideas are the same.
Ah, okay. I get
Okay,
it.
Sasha, explain what you mean, because
I mean, I thought I want to like multiply m of x, my rounded m of x, by some coefficient which depends on the length of x, so that I have a bigger coefficient for smaller x's, so that I can kill this possible difference in these roundings.
no, this I don't understand. So you say some property for the initial measure which make things work.
No, I just want to define.
Or you change the rounding procedure.
Yeah. No, we don't change the rounding procedure. We just apply. We just multiply the results of our rounding precisions by some factors that depend on the length of x.
Okay, but
I mean, what I want in the result. So we want this inequality that rounded m is at least rounded m x0 plus rounded m x1. So what I wanted is that we do not quite have this, right, as of now.
Yeah.
And I just wanted to fix it by doing something so that m of x is actually multiplied by 2, with respect to m of x0 and m of x1. Okay, so my idea doesn't quite work. So I just wanted to set like the actual, I don't know, n of x is 2 to the length of x times m rounded.
No, we shouldn't multiply by exponential factors.
Yeah, I guess that's
and there is no need to multiply. You need just here, if initially for m you have additional things that rounding. So if there is a reserve safety margin.
Sorry to interrupt. Maybe you should first say the plan clearly. So we will start from a different universal measure that has this inequality with some margin built in.
So let's start with a different universal. I will explain how to get it. But imagine that for now that our universal measure has some safety margin. This is not only greater than m of x0 plus m of x1, but also plus this rounding granularity at x. Then of course this change is cannot be bigger than this rounded granularity. So it will not destroy this. This is enough to not destroy it.
This is not clear. Why it's not enough to destroy?
No, of course, if you round with some step granularity epsilon, then the decrease is at most epsilon.
Explain first. What do you mean by rounding granularity at x?
No, so this is to the minus 2n.
Okay.
So it's just at x we made rounding up to 2 to the minus 2n. Steps.
Okay. Mm-hmm.
And if initially we in this inequality we have a reserve of this size, then of course the decrease cannot kill the reserve completely because this decrease is bounded by this size.
Mm-hmm.
So these things decrease, and this is good for us, and this decrease and this is bad. But the size of the decrease is bounded by this reserve safety margin.
So I don't understand actually. You call decrease meaning increase, maybe?
No, when you're rounding, you round to below. Because you still want the sum. No, it's reasonable because you need to have a semi-measure. So the sum should be. So in this direction we have decrease, and this rounding is from below. This decreases, and this is good, and this decreases and this is bad. But the amount of this decrease is bounded by this rounding granularity, and it's taken care of because of this term.
Okay, so from a semi-measure where for which this inequality is through this granularity, you obtain another semi-measure, which is just semi-measure without any
Yeah.
Granularity required.
Yeah. No, which has granularity but has no more safety margin.
Without safety margin.
Yeah.
Margin.
Yeah. But so how do you do that? How do you do this? So you take the universal semi-measure and then add some semi-measure which has no required granularity. And of course you get a maximal semi-measure because you get anything, you get a maximal semi-measure. So you take a semi-measure which is on additional semi-measure, I don't know, G, which on string X is just 2 to the minus 2 length of X. So if this is not a measure because there is 2, but there is a semi-measure. So if it's 1/4 at every, it's 1/4 here, 1/16 here. Yeah. So there is a big reserve. There is a reserve 1/2 here. At every point, half of this semi-measure is a reserve. So no, it should be obvious, but you are looking confused.
I would say that we just distribute that reserve among finite strings. For finite strings, we have some measure, and this is G. And we add M and G.
No,
so
I want to define just the value of the function. Or we also can do like this. We just distribute the reserve on finite strings. But
Right.
I just say that we can consider just the following function G, which is a semi-measure. Here is function G. And which has a good reserve. Because half of the value of G at every point is a reserve.
Okay.
So when adding it to M, it provides all the reserve we need for this. And still we have a maximal semi-measure because we just add it and get something bigger.
Okay.
Okay, so Bruno, is it now clear or not?
It's clear. For me, it's clear.
Yeah. And then there I should make some hand waving, and then we are just consider the semi-measure. And then we should transform it to some bounded use machine which produces it. But for this you just there is a general result how having a semi-measure construct a machine that produces this machine, the semi-measure. And for that we should allocate intervals in the preimage of given sizes of sizes which we want. And since now all the sizes are multiple of known elements, then you can do it easily, not using only cones on only this sets on not to high level, because you consider intervals of required granularity. No, and I realize that without the understanding how to transform a semi-measure into a machine, it makes no sense. But I don't know. Sasha, is something clear or it's completely misleading?
No, it's okay. I mean, you are saying about this part about how to transform a semi-measure into a machine?
Yeah, how to transform a semi-measure into a machine which has this output semi-measure. And if the semi-measure has a good rounding, then the machine will have bounded use. That's what I am saying. Just the standard construction will give a bounded use machine.
Yeah. I mean, it has to be checked somehow, but the standard construction is that you Just when you like receive a new lower bound,
then you should allocate more pre-images to a given string.
Yeah.
If semi-measure of something increases, then you need more pre-images for this thing.
And there will also always be a parent ready that where you can place it.
Yeah, and
because
but
of the
parent
inequality.
has bigger granularity, so there is a place there which can be always. So there is no space loss because of the parent, because it is made of bigger intervals, and we can always find whatever we want inside.
Mm-hmm.
Okay, so now the question, if it's more or less clear how to prove A, then the question is how to prove B, actually. So how to prove this, the theorem, actually, no, I can say different things. So let me see. So no. In fact, if you just look at the proof for image randomness theorem, there would be a gap where it doesn't work for semi-measures. And now with this additional assumption, this gap can be closed. But I don't know. I don't know how to.
Can you just write this false theorem again? I forgot it again.
M. So imagine we have machine T, which transforms uniform distribution to some semi-measure Q is T of P. A T is a bounded use machine. And imagine there is some sequence alpha such that M of x divided by Q of x is bounded for the prefixes of alpha. Then there exists beta such that not beta, omega, such that omega is p random and T of omega is alpha. So now it's true theorem. And true is because of this special additional requirement. So if you take this, Levin also provides a very nice proof of this theorem. But if you take kind of standard proof for image randomness with machines and semi-measures, which, for example, is in the book about Kolmogorov complexity, and actually this is what was missing there. But without any hope that this will be clear, let me say what is the Levin's argument, and then you can just kind of estimate how easy it is or how difficult it is. So I know that Vereshchagin has go to airport now, so just I want to be short. So Levin argument, consider the maximal average bounded randomness test. It's another story, but for now, then the integral, there is a semi-measure tau of x, which is integral of this randomness test with respect to measure p, dp of x for integration is taken over x. So if t is a density of some semi-measure, it's actually almost everywhere a measure, but it's lower semi-computable. And then we compare tau of x. Then we compare the image t of tau and t of p, which is m. And since m is maximal and t of tau is semi-measure, then this is smaller than t of p. And if this is smaller, then these two things are measures of some. These are
so it's just change of variables that you're doing the integral, and then you get a test for q, and then it should be bounded.
No, it's no. So
No?
we actually in this thing we compare the measure of the preimage and integral of tau over this preimage. So if we compare these things for some x, is actually we take the preimage of x and compare the uniform measure of this preimage and integral of tau of test over this preimage. So since this is bounded, the preimage, the deficiency cannot be big everywhere. So there will be a string with bounded deficiency, a sequence with bounded deficiency, which is mapped into this x. And then we can do it for every prefix of x, and then for compactness reasons and using the bounded use property, we show that the limit point of the sequences is a preimage of alpha. So probably it's not clear, but I just want to say that there is, you need to know what is maximal average bounded test and so on. But I just want to say that this is nothing non-trivial. Here it's just a kind of blah blah topological argument without
compactness is clear. I need to think about integral, and I forgot a little bit with change of variables. But
no, there is no change of variables. What is just
you place omega by t of omega. That's basically what you do. But it's forbidden. You have to be careful, so you speak about prefixes.
No, what I'm saying that I consider the measure, which is the image of this tau, and it's a semi-measure, so it's bounded by compared to the unit.
Okay.
And this boundedness just means that we compare two measures and they are both images. So if we compare the measures of a given prefix, we just compare the measures of its preimage they are. And these two measures are just the p measure and this measure with density t. So if the test will be large everywhere on the preimages, then this integral will be much bigger than this. And and the ratio is bounded. So there is some preimage when this is not much bigger. Okay, I'm sorry.
So tau, you use tau to define a measure and you compare it to the universal measure. Then
I compare the image of this tau with the universal measure.
And then this is bounded, so you can find the pre-image where it is bounded, and then it works. So nothing happens when you understand all the parts carefully.
Nothing happens. No, actually, the Levin's paper is like this. There is a page. It's one page, and 3/4 or 7/8 of this page is used by the definitions and notations, and just a big paragraph is introduction, definition, notation, and there is a small paragraph which is called proof of Gacha-Kuchara theorem, which has 3 or 4 lines, and that's all. But of course, it's not so easy to decipher. But I think that I more or less understand what he's doing in any place, and at least I can explain the argument. I even wrote some explanation. But
okay.
Yeah. So, Kolya, is there anything clear or not here?
No. Where do we use bounded use machines?
Because of compactness. So since it's bounded use, the preimage of X is a union of cones. So it's also closed.
You need it to be a finite union. Otherwise,
you need to be a finite union, because otherwise, if it's no, we construct a random preimage of every finite prefix of alpha. But then we need to use compactness, so we use a limit point of the sequences, and it should be random because the randomness deficiency is bounded for all of them, and so it's bounded for the limit. But also we need that the image has bounded is really alpha, and for this we need the closedness of the set.
Good.
Okay.
What can you say what will we have next time?
Но, значит, тут есть there is some student from Ghent, Bruno. You can next time work as a translator from Flemish language to some other language. I assume he should speak. And he explained that he and Gert de Koopman, whom you probably know.
Yeah. So it's about imprecise probability.
Something
and
about randomness with respect to imprecise probability.
Yeah. I felt very guilty that, he helped for my PhD to have no trouble. And I never read his papers. He has 5 or 6 papers about this topic. So it's very good. I have finally a reason to
you
read
finally
all the
you have
papers.
A chance to help his student to explain us what is happening. So I don't know whether it will be clear or not. But I think that it's useful for him if he can produce this thing. I don't know.
And even Miyabi has written something similar like this, and so there are some citations.
If you can explain what Miyabi wrote, it's even better. But this I. Okay, so this is our preliminary plan.
Okay, very good.
And if it doesn't work, then we will have some other thing.
Yeah, and even better news. So I don't have another seminar anymore on Monday evening, so I can always attend Kolmogorov.
Yeah, maybe you want to give a talk.
I will need to prove something interesting.
But you have 2 weeks for that, so please.
Okay, that's good. But I can speak about error correcting codes, I guess, if I understand it again, or Slepian Wolf. No,
okay, you have a choice.
Yeah, that's for later.
You have a choice.
Okay.
No, I don't know. Maybe other people also want to say something. Next.
But sorry, I have little time in the next 2 weeks. It's better if it's in January or February, because then I have more time.
Okay.
So somebody else should speak
flexible.
In 2 weeks. Yeah.
Коля, есть у нас какие-нибудь еще желающие?
Пока нет. Ну, вообще, я, честно говоря, хотел еще раз одну попытку сделать, рассказать про свой треугольник большой.
Нет, но это опасный путь, потому что тогда я захочу попробовать второй раз что-нибудь объяснить про это. А это уже будет полный абзац, я боюсь. Нет, ну ладно, давай попробуем по треугольнике еще раз. Нет,
Нет, ну, в общем, это не скоро в любом случае.
Да. Хорошо. Ладно, тогда спасибо.
Bye-bye, everybody.
Yeah.